Okay, so because of the charges that can accumulate by either gaining electrons or losing electrons, when you have more than one object and they each have their own net charge, let's say there's two objects, one's negatively and one's positively charged. A long time ago, people started to realize these are attracting each other. And the same is true if you have a positive on the left and negative on the right. So it didn't seem to matter where things were. There was some kind of attractive force. They even knew that the closer you bring them, the more intense the pull. You know what I mean? And then they also discovered that if both are positive or if both are negative, it's more of a pushing apart sort of thing. So that's why we say like charges attract, repel, and opposite charges attract. So that's just kind of where that comes from. When people say, oh, opposites attract, that's, I believe, kind of where that idea comes from. Okay, if you want to measure the force, that's where you need the math, right? So it turns out that just like in gravity, the force of gravity was gm1 m2 over r squared, where r is the distance between the centers of mass, right? And m1 is the mass of the first object, m2 is the mass of the other object. This will measure gravitational pull, and this, I think, was known as early as Newton. This is named after him, for sure, although I don't know how well he knew capital G at that time. But anyway, he knew that there was an inverse square relationship, and so he kind of knew this rule. And then the charge version of it is almost exact same thing. Instead of a G, we use a K, and instead of masses, we use charges. Okay, so that measures how strong the pull is. And I didn't write this down yesterday, but K is also known as 1 over 4 pi epsilon naught. We'll talk more about that later. But whether you call it K or 1 over 4 pi epsilon naught, either way, it's about 9.0 times 10 to the 9th. 9.0 times 10 to the 9th. And if you must know the units on K, you can figure those out because you have newtons on the left, right? And then you have this mystery K here. You don't know the units of K yet. But then here you have charge units. And for charges, by the way, we use coulombs. And then on the bottom, we're in the MKS system, so we use meters. So basically what you have here is newtons equals something times Coulomb squared over meters squared. So if you kind of isolate the K, the unknown constant, you end up with Newton meters per Coulomb squared. Newton meters squared per Coulomb squared. So going back to K equals 1 over 4 pi epsilon naught equals 9 times 10 to the 9th, you could put in the units. It's actually Newton meters squared per Coulomb squared. Like I said, who really cares? I mean, the units themselves of K aren't as important as simply knowing how to find the magnitude of the force. Sometimes we will use K, and sometimes we will use 1 over 4 pi epsilon naught. Okay? Now that's in the MKS system, where we're using meters, kilograms, seconds, and so forth. So sometimes we call it the MKSA system. You have not heard this yet because you haven't studied electrical yet. But the A here represents amperes. Amperes, named after, you guessed it, Mr. Ampere. And the ampere is considered a coulomb per second. A coulomb per second. So if you're using MKS units, it's sort of traditional to use coulombs for charge because really it's not the MKS system, it's MKSA system, and we use amperes. So amperes uses coulombs, and therefore coulombs is the right thing to be using. You do not have to measure charge in coulombs. You can measure charge in how many electrons you have. So if you have 5 electrons, you can call it 5 what? 5 elementary charges, we call them. So later we'll use elementary charges also, but for now, we're just going to call them coulombs, coulombs, coulombs for charge. Newtons for force, meters for distance. Okay? All right, so I didn't mention that yesterday, so that's kind of new. And then, because of Newton's third law, F12 and F21 are going to be equal and opposite. So I wrote that here in typed font. But all I'm saying is that when one object's repelling another object, the second object is also repelling the first object. In fact, they're both repelling each other with the same force. Okay? Whether they'll both accelerate or not depends on their masses and other things, but they are always pushing with equal and opposite forces on one another. You guys know that every time you push on a rock, the rock's pushing back at you, right? So if the rock's a small rock, the rock will move and you won't. If the rock's a big rock, you'll move and the rock won't. Right? That's a mass consideration. But the forces themselves are equal and opposite. So if you want to include the direction of the force, you include an r hat. So r hat is a unit vector pointing in the direction of r, pointing in the direction of the vector that points from charge 1 to charge 2. So usually we just go like this, k q1 q2 over r squared. And then we put this little r hat here. And r hat just tells us which way it's pointing. So it might be radially away from charge number 1, or it might be radially towards charge number 1. But the r hat reminds us that it is a radial thing. You're either approaching a particle or you aren't. You're either approaching it or you're going away from it. Those are the two directions. So it's not left and right, it's sort of in and out. In and out, towards the charge, away from the charge. Okay, so we'll talk more about unit vectors later. R hat has magnitude 1, because it's a unit vector. So we could write that like this. The magnitude of r hat is 1. And then some teachers use, for magnitude, the double strike bars. I don't know which one your physics teacher used last year, but I'll just use the double strikes. And then also, if you put it in polar coordinates, think of it this way. You can write r hat as cos theta sine theta. So r hat is its own little vector, cos theta sine theta. And if you find the magnitude, you square root the sum of the squares. And indeed, it's 1, because square root of 1 is 1. So anyway, if we do need polar coordinates, we will use r hat as, instead of, I hat, j hat. So instead of using, I plus j to represent r hat, we'll use cos theta comma sine theta. And if we're in 3D, we might have to go all the way to like spherical coordinates and stuff. So that may happen, but not today. Not today. Okay, let's go to comparing. So we were going to compare which is stronger, gravity or electrical force, right? And just from your common everyday experience, you think gravity is a strong thing. You're like, oh man, I don't want to fall off that cliff, right? But if you fall off a cliff, right, what is it that really kills you? If you fall off a cliff, is it the gravitational force? Let's think about that. So gravity will accelerate you toward the ground. You don't need electrostatics for that. Gravity will do that all on its own. You have mass and so does the Earth. So guess what? You're attracted. And you move fast. After a few seconds, you reach terminal velocity. You don't go any faster maybe. But you will eventually hit the Earth. Now, if gravity is so very strong, it should pull you all the way to the center of the Earth, wouldn't it? So what stops you? What makes you hit the ground and stop moving? Why do you stop moving? What would cause your speed of 120 miles per hour? What would cause that to drop instantly to 0 miles per hour in less than 1 second? That must be some impulse force. That must be some powerful impulse force. Remember, impulse will change momentum, right? And if it's a force executed over a short amount of time, that's a high impulse. So some of you need to go back now and read up on impulse force. Impulse force in your mechanics book, okay? Quick show of hands. So this must be some serious impulse force. So what is causing it? What brings your velocity from 120 miles per hour to 0 in less than a second? Less than half a second. It's electric repulsion. It's electric repulsion. When your body hits the ground, the atoms in your body and the atoms in the ground come together. And what keeps you from going through the ground to the center of the Earth is electrical repulsion. The nuclei of the atoms in your body, your skin primarily, and the nuclei of the atoms in the ground are literally repelling each other. And which force eventually won? Did gravity get you to the center of the Earth? No. Which force actually won? Electrostatic, by a mile. Stopped you instantly. So right there you get a sort of a real subtle glimpse of how powerful the electric force is. So now we're going to actually measure it. So we're going to need to know some things. We're supposed to compare KQ1, Q2 over R squared versus GM1, M2 over R squared. We'd like to compare these. Now, there's two ways you can compare numbers. You can subtract them and find their difference, or you can divide them and find their ratio. You'll notice in our homework that often they want you to divide them to find the ratio. So instead of saying things like, hey, this is 4 newtons stronger, you say something like, oh, this is 4 times stronger. Different language, right? Okay, so we're going to end up dividing these. We're doing electrical and gravitational. So let's just consider it force of electrical to gravitational. So we'll put the division here. We're going to divide these. So the first thing we notice is that the R squareds cancel out. The distance between the centers of the electrons, it doesn't matter if you're measuring gravitational force or electrical force, the two electrons, we'll call E minus and E minus, whether you're thinking about how massive they are and how far apart they are, or whether you're thinking of how charged they are and how far apart they are, either way it's the same distance apart. So that R is the same R. Okay, so this is what we're going to try and find right now. It's going to be the ratio of K, Q1, Q2 over G, M1, M2. That's what we seek to find. And these are electrons, well-known objects in our universe. K we said is 9 times 10 to the 9th. G is 6.67 times 10 to the minus 11th. You probably barely remember that number because it was last year. And I think they just give it to you on the AP test, right? So you don't have to memorize that much if you're an AP physics student. I just remember having to memorize it myself because I actually never took an AP test when I was growing up. So I had it well memorized. And now, what about the charges on an electron? Well, they're both electrons, so they're both negatively charged. And then you're going to have to look this up. What's the charge of an electron? So this is where Siri and Google will just answer you verbally. You know what I mean? So I'm going to ask Google, what is the charge on an electron? I already know, but I'm just going to... So it's 1.60 times 10 to the minus 19th, and that is a Coulomb charge. These are both electrons, so we have another one of these factors. Notice a Coulomb is actually a rather large charge. Basically, you need 10 to the 19th electrons to even get 1 Coulomb. Okay, and then M1 and M2, oh boy, these are going to be real small masses. Let's see how much mass an electron has. So let's go back to Google. This one, I want to say 10 to the minus 24th kilograms, but I honestly don't remember too well. Let's see. What is the mass of an electron? She'll answer out loud if I have my volume turned up, but I told it silent. So it's 9 point, I was wrong. It's 10 to the minus 31st. I thought it was 23rd. Okay, really small kilograms there. That's kilograms. It's actually 9.11 if you're doing 3 sig figs here. Okay, this does need to be typed, okay? And you do get a positive ratio because the two negatives cancel out. Yes? Okay, so if you type all this, okay, so you do not need a calculator for the 10 to the whatevers. So you have 10 to the minus 9th, you have a 10 to the minus 19th, another 10 to the minus 19th, you have a 10 to the minus 11th, you have a 10 to the minus 31st, and a 10 to the minus 31st. So if you look at the top, you basically have 10 to the minus 47. Because you're just combining negative 9, negative 19, and negative 19. That's negative, hold on, negative, oh, this should be a positive 9. Mr. Shore messed up, that's a positive 9. So think of it as positive 9, and you're subtracting 38. So this is 10 to the minus 29, right? Then the bottom is 10 to the minus 11th, 10 to the minus 31st, 10 to the minus 31st. So that's 10 to the minus 73. Okay, so you got the orders of magnitude. 10 to the negative 29 minus negative 73. You can already tell this is on the order of 10 to the, and then 73 minus 29 is 44. So is it 10 to the 44th? Well, it's something near that. So now let's do the other numbers. We had a 9 times a 1.6 times a 1.6 on top, and then we have a 6.7 times a 9.1 times a 9.1 on the bottom. We get 0.04 times 10 to the minus 10 to the 44th. So in scientific notation, you would move the decimal 2 spaces to the right. So now that's just a 4. But to compensate, you would subtract 2 from the powers of 10, so it'd be a 42. So you can see this is a very, very, very large ratio, like really big. And I can't stress enough how much stronger gravity, how much stronger electrostatic force is than gravity. There was another clue all along, by the way. There was another clue all along. Before all this calculation, just look at K versus G. You know what I mean? K is 10 to the 9th. I'm talking positive 10 to the 9th. 9 times 10 to the 9th is 9 billion Newton Coulomb squared per meter squared. G was already 16 orders of magnitude less than that, at least. See what I'm saying? Or about, I mean. So that was a clue already, but until we included the masses and the charges, we couldn't really see the whole truth. The correct ratio is this, 4 times 10 to the 42nd power. So I see some... All right, so let's go now to our next thing. Our next comment is, so the electrical force between two electrons is about 10 to the 42 times stronger than the gravitational force between them. All right, now the scope of Coulomb's law. When are you allowed to use this KQQ over R squared rule? Okay, there is a rule on that. You may not use that rule unless you're dealing with point charges. That means literally charges with no noticeable size or uniformly charged spheres. This is really important, okay? This is also true for gravity, by the way. When you measure a force of gravity or a force of electrostatics, you're supposed to use round objects that are uniformly distributed. For example, let's talk gravity. It's a little bit easier to understand. Let's say you have a ball, and it looks like a regular bowling ball. But when you roll it down the lane, it like wobbles badly. Okay, that means something. That means somewhere in the ball, there might be a pocket of air. Like a bubble was formed when they poured the metal. Or I guess it's a plastic, right? When they pour that plastic bowling ball, they accidentally got a bubble in there. So it's not rolling straight. Okay, you cannot use GMM over R squared as easily in that situation. You can use that idea, but it's probably a little bit risky to just treat it like a single point charge. I don't think all the charges, or point masses, you can't think of all the masses at the center. Okay, so if there's like a little pocket of air in there, you cannot think of all the mass as centrally located. And that kind of messes up the rule itself. The same is true with charges. If you have like a metal ball and you put some electrons on it, we'll talk about this later, but the electrons will all spread themselves out beautifully uniformly across the surface. And then you can use Coulomb's law, because it's all uniformly distributed. Okay? And even if it's like an insulator, and it's got negative charges all throughout it, even on the inside of the volume, as long as it's uniformly distributed, you can treat it with Coulomb's law. Okay, so it works for tiny points, and it works for round objects with very beautifully distributed electrons. And the same is true for gravity. Once you start getting weird shapes like this, and some of the charges, like some of the net charges on this side, and then some of the net charges on this side, and some's positive and negative, and maybe there's more electrons on one side than the other, that's when Coulomb's law isn't meant to be used straight up. You have to use vector math to work with that kind of situation, and integration, actually. Okay? So use it for small charges, one with another. Use it for perfectly round spheres that are uniformly charged. And there are two shell theories. This is very important. Okay, these are also mentioned in the gravity section. If you go back to the gravity section, you'll see them. All right? Anytime you have a shell like this. So the first shell theory just says if you have a uniformly charged object and you're outside over here at point P, you can just think of all of these charges as centrally located. You don't have to think of it as a ball. You can think of it as a dot, point Q or whatever. And then if you are inside the shell, this is the second shell theorem, if you're inside the shell anywhere and it's a hollow shell, you will experience no forces at all. You will experience no forces at all. All right. Transfer of charge to equilibriate. This is important. If you take a metal object, whether it's hollow or not, and you dump a bunch of electrons on it, maybe it's because you rubbed it with something. Or maybe you did an experiment where you charged it up with wires and then you quickly remove the wires. Now it's all charged up, right? So what happens to these electrons? Well, they're on this shell and they're perfectly stuck there. They can't get away. But they're going to do two things. One, they're going to try to repel each other and therefore they're going to spread out. So they're going to definitely spread out from one another to get as far away from each other as possible. And also, none of them will dare enter inside the conductor. So they're not going to go inside the conductor. Because if they go inside the conductor, then they're close to other charges. So if you could kind of see this from the backside, if you could go around the backside and look, you'd see the same picture. All these charges hiding on the backside of the ball. Why? Because there's charges on the front side of the ball, and they're trying to get away from the ball, from those. So every electron is trying to escape every other electron, so they spread out as far as possible. No one dares go inside the conductor, because if they do, then they're closer than they need to be to the other side of the ball. Okay? As soon as you enter a sphere, you're already closer to the other side than you should be, right? So all of the electrons go straight to the surface instantly, and then they spread out completely. So this is another reason why there's no forces on the inside of the ball, because they all spread out and they escape each other and go to the surface. And once they get to the surface, they spread out again and space themselves equally across the surface area. Okay, so that's called transfer of charge to equilibriate, and net charge is distributed over all the surface of the object. Okay? And this is in the case of a conductor, where the electrons can move. Sometimes you can make like a jello kind of thing with charges in it, and then you freeze it as a solid or whatever, and now the charges can't move. They're all kind of stuck close to each other. Oh, well, too bad. But if they can move, they will, and they'll go away from each other, distributing across the surface first, and then on the surface, escaping each other as best they can. Okay? Any questions on that? All right. Almost done with this whole chapter, actually, and then we'll do examples. Non-conductors do not distribute their charges. They can't because the electrons aren't free to move. So you can actually have pockets of net charge. So if it's an insulator, then you can have the object, and have like a lot of positive here, and then just a little bit of positive here, and then like a ton of positive here. But this has to be on an object where the electrons can't move. As soon as the electrons are mobile, man, they are going to distribute things evenly and balance things out for you. Okay. If you see the word current, this is a little early to be talking about current. It's basically the amount of charge that passes through a single point in a certain amount of time. Okay, so current is what it's just what it sounds like. You're standing on the beach and water's flowing by you, right? The ocean's moving the water. Well, when electricity flows past you, you could count how many electrons go by in a minute or whatever, or how many coulombs pass by in a second. If you measure how many coulombs pass by in a second, that's using the ampere measure system. So if it's 1 Coulomb that passes by in 1 second, we call that 1 ampere. Or we just call it an amp. An amp. Okay? So current's kind of a brand new quantity because in the past we've studied things like meters per second and stuff like that. We've never done like mass per second. And now we're doing charge per second. So it's like a brand new thing. And we will need it when we get to circuits.